Hey, this is Mr. A, and I wanted to give you a little bit of a heads up for the quiz tomorrow. When we first started this chapter, we did a pretty tough problem in the very beginning. The monkey suspended on the wires. And in that problem, we had a couple of ropes, and I'm not going to draw a monkey right now. I'm just going to draw a mass that's suspended right here. And I think in this problem we were told that the force of tension in rope 1 was equal to some force, and then there was a force of tension in rope 2 that was equal to something else. And what we had to figure out was what was the size of this mass that would result in a force of gravity balancing those two out. So what we had to do was to draw a free body diagram of that situation where you have two forces going in this direction balanced out by a force in this direction. So I've intentionally made this one longer because this one's having to pull against these two. The way we solved that problem was to realize that this vector, if we broke it down into its components, would have, if this is force of tension 1, this would be force of tension 1 in the y direction, and this would be force of tension 1 in the x direction. We knew, and likewise, if this was the force of tension in rope number 2, there would be a force of tension 2 in the y direction, and a force of tension 2 in the x direction. So this is getting a little bit sloppy here, but what we realize is that these two vectors in the positive y direction would balance out this vector in the negative y direction. And the way we figured that out is that we could figure out what the angles were here, and then we used trigonometric relationships in order to determine what these components were. That was a pretty tough problem. Let me take a step back and maybe give you a little bit easier problem. Let's take a situation where we've got a box or a crate on a surface, and we are going to pull this box off into the x direction. But instead of just pushing on the side of the box or pulling on the side of the box, we're going to do what we usually do in these kind of situations where we have a wagon or a handle or a rope or something. I'm going to attach a rope right here to the bottom of the crate, or just to the side of the crate in any place, and then I'm going to use that to help me pull the box off into this direction. So this is a box, this is a rope, this is me. I am going to apply a force. Now, in order to determine what the motion is going to be at in the x direction, we need to figure out what is the force applied in the x direction. Okay, what is the force applied in the x direction? Well, you'd have to know this angle, wouldn't you? If you knew what the angle was between the rope pulling handle thingy here and the surface, now and if you knew what the force, the total force being applied here is Ft, if you knew what Ft was and theta was, then you should be able to figure it out. So let's draw where we would decompose the total force vector. So here is the total force, and here is the force in the x direction, and here is the force in the y direction. The angle theta is right here. Right? So if you knew what Ft was, and you knew what that angle was, then you can use your trigonometric relationships to figure out what f of x is, this component vector in that direction, this component vector in this direction. Ft, because of the law of cosines, is just, fx is just ft cosine theta. Right? So if ft is the hypotenuse of a triangle, this fx is the side adjacent, and that means that we're going to use the cosine. And likewise, you can see that the length of this vector here is the length of this side of the triangle, and this side of the triangle is the side opposite that angle, so that f of y is equal to the hypotenuse times the sine of that angle. And so now, if you knew the tension here, you could figure out the tension here. You would know what the tension, what the force applied in this direction is going to be, in the x direction. So maybe that's a little. We should have started with maybe a problem that was a little more simpler than the one that we did.